Next, we'll talk about an inferential statistical test called a paired samples t-test, and it's called a paired samples t-test because you'll have samples of participants and their data will be paired, and we'll talk more about what that means in a little bit. But this test is also called a dependent t-test, a dependent samples t-test, a repeated measures t-test, or a within subjects t-test. So there's lots of names for this one particular test because it's used in different kind of contexts. You'll use this test when you have a paired data structure, and I'll show you what that means in a second, and the population standard deviation is unknown. If you knew the population standard deviation, you'd get to do a z-test, but just like with the one sampled t-test here, we don't know the population standard deviation. For this, we'll work with an example of with a research hypothesis. Research question is exam 2 harder than exam 1. So in this case, we have students who took 2 exams, could be you, and then we're going to compare the students' exam scores for exam 1 with exam 2 to see if exam 2 is harder than exam 1. So for this example, the null hypothesis would be that the average score on exam 1 is the same as the population mean for exam 2. And for the paired sample t-test, we're actually going to rewrite this in a way that means the exact same thing, but it actually fits better with how this test will end up working. So here, we could rewrite this as the null hypothesis is the mean difference score for each student, taking their exam 2 score and subtracting exam 1 from it. Those difference scores, on average, are 0, which would be the same as if the 2 exams are of equal difficulty. I want to talk a little bit about what the data would look like if you collected it. So let's say we have our data file like in Excel or SPSS, right? We might have our participant column where we just put a unique number in for each person, right? And then we have, or this would be perhaps students, and then we have their exam 1 score, and their exam 2 scores. All right, these just mean that it goes on throughout all the different students in the class. A paired data structure is when you have 2 measures that are associated with one thing. Here, there would be with students, because this is the student's exam 1 score and the student's exam 2 score. So these data points, these measures are paired. There's other ways you can get paired data. So this would kind of be like a repeated measures, although really it's 2 different measures. If you took exam 1 one time and then another time, then it would be repeated measures. And then you could see if people get better the second time they take an exam, which you'd expect to be the case. Right, so you'd call it a repeated measures t-test if it's exam 1 and then exam 1 again. Here, paired samples is a pretty good name. Another thing that might happen is, let's say I have a male friend and his female friend, and they're saying how much they like each other, right? So we could pair, here it would be like which friend group it is. That would be friend group 1, this would be the guy score, and that would be the girl score. And we could directly compare how much friendship they perceive to have in the relationship to see if the guy thinks they have more friendship or the girl thinks they have more friendship, right? So for whenever you have this kind of paired data structure, and you're only comparing 2 variables, that's when you use a paired samples t-test. And when you have this kind of paired data structure, if you use SPSS, you just put in all this data and you tell SPSS to do a paired samples t-test on exam 1 and exam 2, and it'll do the test for you. In this class, though, you're going to know how to do these by hand, and you'll know how all the distributions work. And really what you end up doing for a paired samples t-test is a modified one-sample t-test. And that's a one-sample t-test on the difference scores. So for example, if we take exam 2, so if this is the difference score, where we take exam 2 minus exam 1, so 90 minus 100, negative 10, 100 minus 90, 10, 100 minus 110, 90 minus 85. And you do that for all the folks. When you're actually doing these by hand, you calculate this difference score before you actually even start doing the test. And this is where, this is the variable you'll actually run your statistical test on. And remember when I said the null hypothesis for this test makes the most sense to say the average difference score equals 0, right? That's referring to these difference scores. And if there's no difference between the exams and their difficulty, then the average difference score here will end up being 0. And when we do this paired sample t-test, really what we're going to do is first transform these raw scores into difference scores, and then do a one-sample t-test on these difference scores with this null hypothesis. So we'll do that next. All right, so next I'll show you how to work through a paired samples t-test and the logic behind how they work. So the first step is going to be saying what the null hypothesis is. So we're going to work with that same example I just used, which is our exam 2. Was exam 2 harder than exam 1? So our null hypothesis for that is that the average difference score for each student in the class, and we'll do exam 2 minus exam 1. The average of those difference scores is 0. So on average, students did just as well on exam 1 as exam 2. The second step we'll do is to draw the population distribution. So that'll be here. So this is the population distribution, right? This is a frequency distribution like all of them. This assumes that the null hypothesis is true, right? So we're hoping to find that our sample didn't come from this population. A difference here compared to the one sample t-test, and I'll try to do these differences in a different color, is these are now going to be difference scores. They're difference scores for individuals. So each student in the class would have their own difference score, their exam 2 score minus their exam 1 score. So we're going to assume this is a normally shaped distribution. The population mean is going to be determined by our null hypothesis, right? And so it says 0. That's the mean difference score. And the standard deviation of this distribution, sigma, is unknown. If we knew it, we'd be doing a z-test instead. And when we don't know the population standard deviation, we're going to estimate it based on the observed samples standard deviation. We'll finish the population drawing in just a second, because we don't know the population standard deviation, so we need to know information about our sample. Right, so the third step we'll do is we'll draw the observed sample distribution. So that's going to be down here. This is going to be, as always, our observed sample data. And although when we collect our data, when we have our students go through the class, exam 1 and exam 2 are separate scores for each student. When we're starting to actually do our paired sample t-test, we're already going to have subtracted, for each student, we'll have subtracted their exam 1 score from their exam 2 score. So if a student got 110 on exam 2 and 100 on exam 1, the difference score is 10. And that's what this is going to be. This is going to be those difference scores. Right, and notice that the observed sample data has to be the same type as the population data. Right? These are exactly the same. They're both difference scores. So down here we have exam 2 minus exam 1. So these are the difference scores. We got negative 10, 0, 10, 20, 30. Really, so these could be lined up, so this 0 is right by this 0, but I didn't quite draw it perfectly. We'll say this is what our students' different scores look like. And we'll use an n for the different scores is 100. So what these 100 different scores is comprised of is 100 exam 1 scores and 100 exam 2 scores, right? And it's the different scores between those as our actual sample size. One way to hopefully keep this straight is if you think about doing the paired samples t-test, when you're doing it, you've already transformed these original raw test scores into the different scores before you even start. So there's 100 different scores that we're actually analyzing. We're not looking at 200 exam scores. We're looking at 100 different scores. So try to think of it that way so you remember the correct sample size. The mean, we'll say, is 10, and the standard deviation, we'll stick with 10. So nice, easy numbers to work with. Now that we know what our sample data looks like, we can figure out what we'll use here. So we're going to estimate the population standard deviation to be the standard deviation of our different scores, which in this case is 10. So our best guess is the population standard deviation is 10. So that's what we're going to assume as we're doing the paired samples t-test. The fourth step is to draw the sampling distribution. And throughout this whole class, the sampling distribution is always going to be in the middle here. So this is our sampling distribution. All right, this is the kind of sample means we expect if the null hypothesis is true. So we'll call this our null hypothesis sampling distribution. And just like usual, it's going to be t distribution. And this time, what we're going to do to create this is we have a sample size of 100. So we're going to take 100 randomly sampled individual values from here, individual scores. So these are different scores now, 100 different scores. And we're going to calculate, for those different scores, we're going to calculate their mean. So d bar is going to be the mean of those different scores. We're going to take that mean and put that down here. And that would be for our first sample. Then we'll do that for another sample of 100, calculate the average of those 100s, and that would go down here. And we would do that for all possible samples of 100. So what this is going to be is the sample means that we expect from this population, if the null hypothesis is true, due to random sampling. So this is exactly the same thing we did with the z-test and the one sample t-test. So it's the same process here. But now the things that are in here just are a little bit different. These are now mean different scores. But don't get hung up on these slight differences of being the slight differences compared to the one sample t-test, right? These being different scores. Overall, the logic is identical, and we're putting slightly different symbols on here, but really they're just superficial changes. We're just taking 100 scores from here, and we're calculating the mean of those and putting that down here, and we're doing that for all possible combinations of 100, just like we've done in the past. So the mean of this distribution is going to be the same as this one. And this will now be the mean of the mean different scores. And the standard deviation is going to be an estimate based on the sample. But it's going to be from the means. So we'll do just like we did before. Take the standard deviation up here, divided by the square root of the sample size. So our standard deviation is 10 divided by your sample size of 100. And so we get 10 divided by 10, 1. So our standard deviation of this distribution, the standard error, is going to be 1. The fifth step is to identify the critical region critical region. And recall that's the area on the sampling distribution where the samples are so extreme that if we observe a sample that extreme, we will decide that our sample wasn't from this population because it's such an unusual sample from this population, it must have come from another population. In this case, it would be a population where the difficulty of exam 1 and exam 2 is not the same, that one exam is harder than the other. So for identifying our critical region, the first thing we need is our alpha. And we're going to stick with alpha of 0.05 throughout this whole class. We need to decide if we want a one-tail test or a two-tail test, and we definitely want to do a two-tail test for this, and pretty much every statistical test we'll do in this class and in our whole lives. So because it's a two-tail test, we're going to split this 0.05 across both sides of this. So I'll color it in here. Right, this is a symmetrical t distribution, and we're going to put half of this on each side. And then what we need to do next is look at a t table, and that'll tell us for alpha of 0.05 two-tailed test what the critical values are. These are going to be t statistics. So a t statistic is a z-score on a t distribution. So I'll get my t table here, and so we'll need our degrees of freedom for that. Our degrees of freedom formula, as usual, is n minus 1. N equals 100 minus 1, so our degrees of freedom is 99. So for degrees of freedom 99, we'll go down the degrees of freedom column on the table. There's no 99. The closest thing is 100 or 95. We can't go to 100. That would be like having more participants than we have, which is unfair, so we're going to have to go back up to 95. And then we've got to find the column for a two-tailed test with an alpha of 0.05. There it is. So our t critical is 1.986. 1.986. And over here would be the negative version of that, negative 1.986, right, because it's a symmetrical distribution. Okay, so now our critical regions are identified. So when we calculate the z-score of our observed sample mean on this distribution, if it's more than 1.986 standard deviations away from the mean, we're going to decide our sample is not from this population. So I'm going to write the t critical values. We got here plus or minus 1.986. Step number 6 is to calculate the test statistic. And remember, these test statistics are almost always the z-score of your sample mean on this distribution, and they definitely offer t-tests. So that's what we're going to do now, is we want to find out for our observed sample mean, where is it on this distribution? And is it so extreme that it's unlikely to have come from the population that's assumed under the null hypothesis? So to find out if our sample, observed sample mean is so extreme that it probably didn't come from this distribution, we're going to calculate the z-score of our sample mean on this distribution, and that z-score is called a t-statistic. It's our observed sample mean minus the mean of the distribution divided by the standard deviation of that distribution. Right, so this is a very familiar formula, other than I'm just putting slightly different like letters up here, but try not to think about it in terms of these specific letters. Just think of it generally. It's the same general process we've been doing the whole time. This is just another z-score. So now I'll plug in our values. We got 10 minus 0 divided by the standard deviation. So our t-statistic is going to be 10 divided by 1 is 10. So our t-statistic is 10. That means our observed sample is actually 10 standard deviations over to the right. So this is 1, 2, 4, 5. So it's about right there. So from this population, if you randomly sample from it, this is where most of the sample means show up. Our sample mean showed up way over here. So that's an extremely unlikely sample from this population due to random sampling. The next step is we're going to make our decision. And you can either decide to reject the null hypothesis or fail to reject the null hypothesis. And recall, for this class, and whenever you're doing these by hand, you always use the same criteria for deciding. If your test statistic is more extreme, larger than your critical values, right? And this is the absolute value, so it doesn't matter if it's positive or negative. If you just turn them all into positive values, if your t-statistic is larger than your t-critical, you reject the null hypothesis. Right, and so in this case, our t-statistic is 10, t-critical 1.98. 10 is larger than 1.98, so we reject the null hypothesis, right? We decide that the exam 1 and exam 2 are not equally difficult. We decide one is more difficult than the other. We reject the idea that at the population level, the two exams are equally difficult. All right, now that we've decided to reject the null hypothesis, there's one final step, which is interpreting the findings. So for this, the most simple way to interpret it is just to figure out which exam was harder than the other one. So here what we did is we took exam 2 scores and subtracted exam 1 scores. So a positive value means exam 1 is harder than exam 2. For example, if we put in 100 here and 90 here, the different score that you get if exam 1 is harder is 10. So positive values mean exam 1 is harder. You have to think this through, right? And in this case, the average difference score was a positive 10. So exam 1 was harder than exam 2. So if we do the statistical test, we reject the null hypothesis. We decide exam 1 is harder than exam 2. And for our interpretation, we can go one more step and actually calculate the observed effect size. And for these t-tests, the observed effect size is the z-score of our observed sample on the distribution up here. So this is Cohen's d. And we've got our observed sample minus this mean divided by the standard deviation. So this will tell us how many standard deviations our sample mean is away from the population mean. We'll plug our values in here. So our observed sample mean is 10. The mean here is 0. Standard deviation is 10. So 1. So Cohen's d in this case is 1. So our observed sample is 1 standard deviation over here. So it is 1 standard deviation over here. So remember, what we're really doing here is we're using our sample mean as a point estimate, our best guess at the population mean. And so we're guessing that really this is probably where we got our sample from. And the effect size of 1 is a large effect size. Remember, for Cohen's d, there's small, medium, and large effect sizes. And small is plus or minus 0.2, medium is plus or minus 0.5, and large is plus or minus 0.8. So a 1 effect size is a pretty large effect size in psychology.